Hello everybody, this is going to be another statics video, and in this video we're going to be covering centroids. We're going to go ahead and do an example of a centroid of a shaded area bounded by two lines here. So in order to start this problem, let's go ahead and write our equations for centroid. So for x bar, we know that's the integral x tilde times dA divided by the integral dA. Similarly for y bar, integral of y tilde dA divided by integral dA. Okay. Now with that, we're going to go ahead and do x bar first. So what I'm going to do here is I'm going to draw our x and y coordinate system a little bigger. And we'll call this line y1, call this line y2. Okay, so to find x bar, what we're going to have to do here is let's take a small rectangular strip here. We know that rectangular strip is going to have a thickness of dx here. And its height is going to be the height of y1 here, so from here to here, minus the height of y2 from here to here, because that's the height that's left in the enclosed area. So that means that the overall height here is going to be y1 minus y2. So this is dx, this is y1 minus y2. So with that, we can say that the area of this differential element is now going to be dx times y1 minus y2. And what we can do here as well is we can substitute our line equations of our lines into our y1 and y2 respectively. So let's go ahead and do that. So we're going to have dx times x minus 1 over 100 times x squared. And that's all equal to dA. And what we're going to do is we're going to substitute this dA in for the dAs that appear in our x bar equation in order to go ahead and integrate and solve for x bar. One other thing to note is our x tilde here from this equation. So in order to get x tilde is represented as the moment arm from our y-axis to our differential element. So this is x tilde here. And in this case, we can say that x tilde is some arbitrary x distance away from the y-axis, which makes it easier for us. So now we can just go ahead and substitute our dA into the x bar equation and rewrite x tilde as x. So let's write that here. Okay, so if we go ahead and do that, we're going to have x bar is equal to integral x minus 1 over 100 x squared dx, all divided by integral x minus 1 over 100 x squared dx. And in terms of the limits of integration here, so they're telling us it starts here at the origin and it goes all the way to the ordered pair 100, 100. We know that's in millimeters. So that means our x is going to go from 0 to 100 millimeters. So our limits will also be that, 0 to 100. Okay, we can also distribute this x in the numerator. So from 0 to 100, x squared minus 1 over 100 x to the third dx. All that over is 0 to 100 x minus 1 over 100 x squared dx. Okay, and then from here, it's going to be simple calculus to solve the rest here. So let's go ahead and do that here. So x bar is going to equal 1/3 x to the third minus 1 over 400 x to the fourth from 0 to 100 divided by 1/2 x squared minus 1 over 300 x to the third 0 to 100. And if we go ahead and evaluate that, we're going to get a value of x bar that is approximately 50 millimeters. Okay, so that's our x bar here. And then similarly, we can do the same approach to get y bar. Okay, we're calling this y1. That's y2, like before. Okay, so similarly to our x bar, for our y bar, what we're going to have to do here is we're also going to draw a rectangle, but in this case we're going to draw a horizontal rectangle. So if I explode that horizontal rectangle out here, we're going to say that that rectangle has a thickness here of a dy, and the length here is going to be, it's going to be x1 minus x2. So that right there is the distance from y axis to this line out here, this y2 line, minus from the y axis to this y1 line here, because that is going to leave us with the resultant length inside here. So let me redraw this. So if this is blue, and that's black, what it's going to be here is it's going to be x, the blue x, minus the black x length. Okay. Now with that, we can also rewrite the area, or write the area, I should say, of this rectangular piece as dA times the length and the base multiplied together, which would be dy times our blue x, so let's write blue x, minus the black x. And then the black x, or I'm sorry, the blue x we can represent in terms of y, since we're going to be integrating a dy here eventually. So dy, let's write our blue x equation out here. So if we want to solve for x here, simply just move 100 over, take the square root. So that's now square root of 100y minus x. And you can simplify that even further a little bit here. Okay. And again, for the y tilde, similarly to the x tilde in the other example, we know the centroid of this element is an arbitrary y distance away from the x-axis here. So the centroid here, this is our y tilde, and we can say that that's some arbitrary y distance away. So when we substitute down here, so let's do that here. When we substitute, so let's rewrite our equation here. So let's go ahead and substitute now. We're going to have an integral of y times our dA is now dy 10y to the 1/2 minus y all over integral of dy times tan y to the 1/2 minus y. Okay. And from here, we can distribute the numerator. We'll be left with tan y to the 3/2 minus y squared dy. The denominator, tan y to the 1/2 minus y dy. And similarly to the other example, for our limits, we know this is going from 0, 0 to 100, 100. So our y distance is going to go from 0 to 100. So those are our limits right there. And then if we go ahead and actually evaluate this, so I'm going to do the integral right now, we'll end up with 10 times 2 over 5, y to the 5 over 2, minus 1/3 y to the 3rd, 0 to 100, 10 times 2 over 3, y to the 3/2, minus 1/2 times y squared, from 0 to 100. And if we go ahead and do the algebra and evaluate that out, we'll get a y bar of approximately 40 millimeters. So what that means now is that our x bar is 50 millimeters, y bar is 40 millimeters. So this right here is our final answer for the x bar and y bar for the problem. I hope you guys enjoyed.